Up and up. Okay, there we go. Right. Let's start the next lesson now. You got that? Guys, you got that? Let's start work now. Okay, so in this picture, work is being done. What things are needed for work to be done? So if we're saying work is being done, what things do we need? We need a force, yeah. We need a distance. And also, usually the force is applied over an area. Anyways, you kind of have an intuition for this already. But in physics, we have an exact definition of work, which I heard you say already, Bello. So what is work done? Yeah, the work done by a force acting on a body is the force along the direction of displacement multiplied by the displacement. Mathematically, quite simply, work equals Fx, where W is the work, F is the force, and X is the displacement. So you can write that down. Yeah, W is work. Okay, if you got that? Yeah? No? Okay. Okay, you got that? So, what would be the units here of work if we look at the formula? Newton meter, yeah. Newton meters. And a Newton meter is also called a joule. We say that 1 joule of work is... Now, actually, before I continue, they sometimes ask you this in the exam. Define what a joule is. So 1 joule of work is when 1 newton of force displaces an object by 1 meter in the direction of the force. And 1 joule is the same as 1 newton meter. Okay, so they sometimes ask for this in the exam as well. This is actually common. I've seen this a few times. You should write that down. Got that?
No, next second.
Okay. Okay, you got that?
Wait a second.
Okay.
Three more. Three more. Yes, okay.
Great. Okay, so next now, here's some little examples just to get us thinking. So where and what is doing the work in each of these examples? So a mother lifting her baby up from the ground. What is the force here? The lifting force, isn't it? Yeah. And the direction? Upwards. Let's just say a woman. A woman pushing a large box across the ground. Yeah. The horizontal force. And the distance? The horizontal movement. A man kicking a football. What is the force? Well, the force on his foot. And the distance? No. What's the distance? No. No, it's not. It's not this distance. No. No. What's the distance? Yeah. The distance is how far the ball travels while it's in contact with his foot. So maybe 50, 60 centimeters. The work done is the force times the distance, but it only makes sense if it's the distance while the force is actually moving it. Once the ball leaves his foot, he's not doing any more work to the ball, is he? He's not even in contact with the ball. Yeah? Did you get that? It's the distance while he's in contact with it. Okay? If you push something and then stop pushing it, are you still doing work? No. Even if it's still moving. Right? A child hitting the wall. So the force is in his hands, obviously, but what's the distance? No, there must be some distance because he is doing some work. So the distance is his compression in his hand. That's the distance. Okay. And a father carrying his child, what's the force? Is in the arms, and the distance? Mm-hmm. Not zero. Again, just like the last one, not zero. Yeah. Compression maybe in the shoulders, the vertical upward distance then. Okay. Anyways, I'm just making the point that it's not always clear, but most of the time it's clear. The last example was interesting because no work was being done to the child. The distance was zero. Now, I know in real life that's not true because as the father's walking, he's kind of moving up and down a little bit. So there is some work being done. But we only care about the work being done in the direction of the force and the movement of the force. We want the direction of the force and the movement to be the same. That's all we care about. This means we may have to resolve the force vector. In particular, we have to resolve it if the force is at an angle. So, for example, if I go back to the box and the person is pushing the box, well, if it moves a distance d and there's a force F, what's the work done? Fd, quite simple. Now, if the force is at an angle, then we only care about this component because it's in the direction that it moves. And if this is theta, what's this? F cos theta. So what would be the work? Fd cos theta. Yeah? So that's worth keeping in mind. Here's a simple example. A woman pushes a 1,000 kilogram box along a smooth surface. The block starts at rest and reaches 1 meter per second in 5 seconds. How do you get the acceleration here? What do we use? No. What do we use to get the acceleration here? Yeah, UVATS. right? Yes?
Yeah.
How do we get the distance travelled? It's the S. How do we get the force? F equals ma. How do we get the work? Yeah, which in this case is Fs. Yeah? And then lastly, if she pushes an angle of 10 degrees, yeah. Okay, see how quickly you can do this. It should only take you a minute. Okay. So firstly, what was the acceleration? I think it's 0.2 meters per second squared. Yes? What was the distance travelled? Well, that is S2, okay? And the force... What's that?
Meters.
Everything here is meters.
Standard units.
Yeah. What was the force being applied? So F equals ma, so that's 100 times 0.2, so that's 20 newtons, isn't it? How much work was being done? Well, that's 20 times the distance, so that's 40 newtons. Yeah. And lastly, you just have to do 40 cos 10. So what's that? 38, is it? 39? 39 newtons. See? So easy, you barely need a calculator. Right. Continue. Continue. So, there is another element at play here. So, for the ballerina now, why does standing on 1 foot feel more difficult? So why is this more difficult or more painful? Center of gravity is the same? Is her weight the same? Yeah, so, but why is this harder? Smaller area. Smaller area. Right? I mean, it's not only that she's standing on 1 foot, she's only standing on two or three toes, maybe. So, I mean, that's... yeah, well, you can Google it later, but if you want some horrifying images, just go to Google Images and type in something like ballerina's toes. It's not, no, don't do it now. It's not pleasant. So she has all of her force in, I don't know, this much area maybe? Yeah? So that's quite painful. So this gives us this gives us our next idea. So it's not only force that matters, but what else? Yeah, so I'm sure some of you know this already. What is it when you mix force and area together? What new idea do you get? Oh, come on. I know someone knows what you get when you mix force and area. What's the next concept here?
Energy.
No?
Pressure.
Pressure.
I said these.
I thought he said energy. What did he say? He said energy. Yeah. He said energy, didn't he? That's what you heard as well? Yeah. Not pressure. Anyways. Pressure. So what is the formula for pressure? No. Yeah. Pressure is force applied at right, my slides are stuck at the moment, force applied at right angles per unit area. So what's the units? Yeah, Newton per meter squared. This is also called a... Does anyone know the other name for this unit? Pascal. Yeah, which is written as PA. Yeah, okay, can you write that down? See if I can find this. Okay, if you got that, I'll give you an example here. I'm trying to find an area here for you. Here we go. No. We'll have to estimate it. Okay. Let's have a look at an example. Right. So we have our ballerina here. Here we go. On surface here. Right, we need to estimate two things. First, her mass. Right, what would we give her? What would be her mass? 80? I don't know about that. 80? Yeah. Could be anywhere from 38 kilograms to 58. 38 to 58. So let's make her 59 then, we'll say. 59 kg. Now we'll have to estimate the area. So if we think about her contact here roughly being like a rectangle in shape.
4 centimeters.
Yeah. I'm thinking something like this too, perhaps. Yeah, maybe.
4.
Let's say 5 and 2, we'll say. Something like this. Yeah? As the contact area. Okay. So, what I want you to calculate now for me is the pressure. Okay, so the area is 0.05 times 0.02. So the pressure is 59 times 9.81 divided by 0.05 times 0.02. So what's that pressure? Say again?
5, 7, 8, 7, 9.
Yeah?
0.9.
0? Really? Okay, so that is 579 kilo pascals, yes? Oh, that's a lot. That's a lot of pressure, like really 579 kilopascals. It's like, how can I put this now? I'm trying to think what would be comparable to.
Make it up, Pascal.
Yeah, it's no, much worse than that. it's like having 57 tons on your body. Because think about, we'll look at a comparison, okay? So have a look here. Here you are lying on the ground, and you have a giant weight on you, and we'll say this is 50,000 kilograms, and the area we'll say is 1 meter squared. What's the pressure here? Well, it's force over area. Would it be 50,000 times 9.81 over 1? So that's roughly 5 zeros. Roughly. Which is 500 kilopascals. Is that a similar number we got? Yeah. Yeah. So the pressure would be comparable to this situation. Yeah? Now, if you're squeamish, you know what I mean by squeamish? If you don't like looking at disgusting things, then maybe you don't want to look, because I'm going to show you what ballerina's toes look like, to give you a good picture of how much pressure this is. So if you want to close your eyes and look away, now's your chance. But if you're morbidly curious, you can have a look now. Yeah. Pretty, pretty rough going, huh? Yeah. Okay. Yeah, it's so easy, isn't it? Right, okay. No. Okay, so there's a few minutes left. I'll let you try these questions in the book. Sometimes these questions are at angles, but that really, I mean, you saw with the last example, being at an angle doesn't change much. You just have to get the component, that's all. Okay, so there's 5 minutes left. If you can get a start on your next homework then.